the zeros in this function? Well, the only way it can be zero is if this equals zero or this equals zero, right? Because when you multiply two numbers, the only way you get zero is if one of them or both maybe is zero. So those are both equations you can easily solve. Okay. Now, I'm not going to write out the detail of solving a linear equation anymore. Unless there's weirdness to the equation. Okay, the y-intercept x equals 0, y equals -4 times 9 squared. Of course, you want to do the substitution step, 0 minus 4 and 2 times 0 plus 9, but you know that 0 minus 4 is -4. And 2 times 0 is 0, so 2 times 0 plus 9 is 9. And you get -364. If this is your function. And if it's not, well, you just substitute 0. Okay. Y-intercept is 0, -364. Y-intercept is always a cause for great joy because it's easy. Okay. And the zeros are generally not that difficult if the function is already factored. Okay. Now, as x goes to infinity, well, large positive x, everything's positive. Okay. All factors are positive and large. So y goes to infinity. I'll leave myself enough room. As x goes to negative infinity, well, actually, is what I consider all factors. I'm going to say that x minus 4 is negative and large. Two x plus 9 squared is positive and really large. So y goes to negative infinity. That's your reasoning. You always ask 4 questions on a polynomial. What are the zeros? What's the x of the y-intercept? What happens as x gets really large? What happens as y gets really large? Whether positive or negative. Okay. So x, what happens as x goes infinity? And I think so what happens when y is large? Saying things without even realizing what I said. Say it right. As x gets really large in the positive sense, or x gets really large in the negative sense. In other words, x goes toward infinity as x goes toward negative infinity. What happens? You can always reason it out. Now, there are rules for the degree of the equation and all that stuff. I don't like memorizing rules when it's fairly easy to understand why the rules work. Because if you don't understand why they work, if your memory fails you, you're stuck. Okay? If you understand why x approaches or y approaches infinity as x approaches infinity, then you don't need a rule. Now, ideally, you memorize the rule and you understand why it works. That way you're doubly protected. If you forget one, you can use the other. Well, there we go. It's a great rule. Try to understand why it works. So now we do the graph. First of all, negative 364 means you guessed the point. 0, negative 364. A 0 at x equals 4, a 0 at x equals negative 9 halves, which that's, yeah, we could write that as a mixed number, -4 and a half, or negative 4.5 if you like. But we can put 4 here. So that would be the 0.40. And just a little further on the left side, we have negative 4.5, 0. The long run behavior, x gets really, really large here, is y gets really, really large as x goes to infinity. So it's going to go up like this. Over here, it's going to go down really fast. So the graph has to go through this point, and this point. And it has to end up, has to start down and end up. Okay. Now your graph can't come through this point because the only places it can go through the x-axis are the points where it has zeros. In other words, if it goes through the x-axis, that means that this term for that value of x is going to be 0, or this expression is going to be 0. So we come up through here. If we try to go down through the x-axis to get down here, it's not going to work because we go through the x-axis here at a point where this isn't 0. Well, we look at the multiplicity. This is 2x plus 9 squared. 2x plus 9 squared is just your squaring function transformed. It's got a vertex. And the vertex occurs when it's 0, it turns out. So that this thing behaves like a parabola in the neighborhood of this point. So you have a graph comes up like this. That's at this point, it turns around, just like a parabola. Then it turns around and goes back down. Maybe it doesn't go down this far, but maybe it does. And that comes back up like this. I didn't draw that very well. Probably doesn't come down that far. Okay. So it's not really a smooth curve there. It's almost a point. That's not a good idea. But I'm not going to get picky about that. That's something you can worry about when you take calculus. Okay. If you had a graph even as bad as the one I just drew, it's okay. Hopefully you drew a better one. One thing you don't do is you don't try to make this your low point. There's no reason it should be. You don't know where the low point is going to be, and you don't have the means to figure it out. It's fairly easy to figure out what that low point ought to be once you know some calculus. Okay. So along about the second month of your calculus course, you'll know how to do that. But right now, not part of this course. We don't worry about it, but we don't assume that this is the low point because it almost never is. Okay. So you draw it in a sensible way. Maybe it goes through this point before it turns out to go up here. That could make sense. Or maybe it has a low point kind of close to here and then comes back up. It probably doesn't go back. Okay, well, that's it. That's all there is to graphing a polynomial. Now that's, a few steps and there are things to understand. You want to be sure you understand those things because before long, we're going to be graphing rational functions which have vertical asymptotes and stuff. And it's a little more complicated. Okay. So we have another one. And it illustrates another thing which can happen. So let's say we have y equals. Okay? First thing, actually the y-intercept is not a bad thing to do first with the zeros. It doesn't really matter what order you do these things in. Each one is independent of the others. But since the y-intercept is easy. If x is 0, you're going to end up with 17 cubed, negative 17 cubed, plus 9. Now, I just put myself in a position of having to cube 17. Well, 17 squared is 289. And from there on, well, 17 times 300 would be 5,100. 17 times 11 is 187. So 3,100 minus 187 is 2913. Then I got to multiply that by 9, doggone it. Okay, and I'm probably wrong already. Okay, so I'm going to say I don't want to think that hard. This is around maybe 26,000. Okay, not just I don't want to think that hard. I don't want to take the time to think that hard. I don't want to have you see me get a headache. It's a pathetic sight. So we'll stick with this. Okay, something like that. Punch it into your calculator. Maybe I was close. Oh, wait a minute. Oh, it's 1,500. It's 49. That's going to be like more like 44,000. Makes sense? Yeah. Okay. I got from 4913 to 2913. Never mind. Okay. Don't try to do it, Chris. Okay. Now that's going to be a really big negative number, but that's not a problem. We just draw the axis, slap a point in the negative x, y axis and call it negative 44,000. Okay. Doesn't matter what the number is. But then that gives you a scale for your y axis once you do that. Okay, well, the x-intercept. Okay, there we have it. Now, whatever you have here, if you solve this equation using the quadratic formula, you're going to find that you get a negative under the square root, so there aren't going to be any zeros. Okay. X is 17/5. You want to do that in decimal form, be 3.4 or 3 2/5. Not real because of the square root of negative 35. So there are no real zeros. So there's not going to be any x-intercepts to come out from this. Okay. I'm not going to write out all the reasoning. If x is really big, x squared is really, really big. And the cube of 5x minus 17 is really, really, really big. Okay. So when you multiply these out, this gets huge. So y is going to be fast. Okay, well, as x goes to negative infinity, y is going to be the cube of a big negative number. But x squared is going to be way bigger than x. It's going to be positive, right? So you have a big negative number times a big positive number. And there we have it. So now if we check our graph, here's the point 0, negative 44,000 or something like that. And we have where is it? 2.4, x equals 3.4. .40 here. And this thing is negative this way and positive this way, right? So that means it comes up from way down here, goes through this point, and then it goes up and it's positive. But when it goes through this point, it acts like the x cubed graph. So when it comes up here, it's got to level off before it goes back up. It's going to come up really fast, and it's going to then kind of level off, and then it's going to go back up. So it looks just like an x cubed graph shifted over. Doesn't look just like it, but it has the same general appearance as an x cubed graph. Of course, this is cubed. Near the 0 that you get, near x equals 3.4, this thing acts just like the x cubed graph does at the origin. Okay, so that's kind of it for graphing polynomials. Now, this leads us into the next assignment, which is actually a pretty easy assignment. Okay. And in this assignment, you're going to be asked to find complex figures. Okay. Now this can get a little bit involved. Keep your wits about it. It's not hard at all. Okay. Let's look again at the zeros. Or the function we just did, which is 5x minus 17 times x squared plus x plus 5. Yeah. Well, 5x minus 17 is 0. So x equals 3.4. Now we're going to actually complete this quadratic formula. Okay, we get -1 plus or minus the square root of -35, and that's divided by 2. Square root of -35 is the square root of -1 times the square root of 35. This 35 is -1 times 35, right? And the square root of this times that is the square root of this times the square root of that. That's over 2. Now, what's the square root of 35? 35 is really close to 36. Square root of 36 is 6, right? So the square root of 35 is approximately 5.9. Yeah, not exactly 5.9, but it's close. It's okay, this is -1 plus or minus 5.9 times the square root of -1 divided by 2. And that would be -1 plus or minus 5.9i over 6. I being the square root of -1. And that's something that should be familiar to you. Okay. As soon as you study quadratic functions in algebra, you start doing this. Okay. But if it isn't, well, your book is going to clarify it for you. Okay. Materials will clarify it for you. Square root of -1 is not a real number. It's an imaginary number, and we call it I for imaginary. Okay. And then, of course, we can divide both of these by 2. Approximately 1/2 plus or minus 2.85, but that 5 isn't something you can take to the bank. Could be, let's see, interpolate that. It could be 8.3, 8.4, something like that. Okay. So that's just a ballpark estimate. You use your calculator to do the square root of 35. And then you think. If your calculator tells you the square root of 35 is 46, you are thinking about what the square root of 35 ought to be. Because it's a simple number, it's close to a perfect square. You know the 35 is between 25 and 36, so the square root's going to be between 5 and 6, right? And you know this is closer to 36 than it is to 25, so the number is going to be closer to 6 than it is to 5. So if you get a number like 42, it means you punch your calculator wrong or something, your calculator went haywire, which is unusual. That probably wouldn't happen. You could punch something wrong. Okay, don't believe everything your calculator tells you. Think about what you're looking at. Okay, so anyhow, there we have it. Now, that doesn't have any significant effect on the graph, but that's actually important for a lot of applications. The study of functions of a complex variable is one of the most highly developed and important aspects of higher mathematics. Okay, I spent 3 years concentrating on it in graduate school. Okay, and you just really scratch the surface. So it's a big deal, and I can't explain to you why it's a big deal unless you've had a calculus course and differential equations course. Okay. So take my word for it, it's a big deal. If it wasn't for theory of functions of complex variables, we would not have a technological society. Couldn't have done it now. Okay. We might be better off if we wouldn't have a technological society. Okay. So the zeros the set of zeros is a set okay, using the approximation, which isn't completely accurate. I suspect that's off by at least a tenth. Okay. That tells you kind of what the numbers are, how big they are. But if you want it exact, you put it in this form, and it's not square root of 35, square root of 35. Put in this form. Now that's really easy. All you got to do is imitate examples a couple of times, and you get used to it. Okay. You just plug the numbers into the quadratic formula and take what you get. So that's kind of where complex numbers come from, at least the place that you understand best. That's really pretty much where they do come from. Okay. Multiply complex numbers using distributive law. And the fact that I squared is -1. If I is the square root of -1, when you square that, you do the square root of -1 times the square root of -1, which gives you -1. Okay, that's what square root and square means. So we use the fact that use the distributive law on this fact, and I can illustrate that with this one simple example. Okay. Somebody pulled up some fingers on one or two hands. Okay, we got 5. Okay, somebody hold up the number of fingers in one or two hands. 2. Okay. Somebody else. 10. I'll do a minus here. Another set of fingers. Okay, 4. Doesn't matter what the numbers are, it's easy to multiply these. If you remember the distributive law, remember that I squared is -1. Neither of which is very difficult. Okay, so by the distributive law, that's 5 times 10 minus 4i plus 2i times 10 minus 4i, which is 5 times 10 minus 5 times 4i, 2i times 10, plus 2i times -4i. I was tempted to multiply it out because I, as usual, was running out of room. Okay, makes sense? That's your distributive law. Something we've done over and over again. Make sure you understand the distributive law. But now we just multiply. 5 times 10 is 50. 5 times 4 is 20. Of course, we got the negative. 2i times 10. 2 times 10 is 20, so that's 20i. Oh, look at that. Your eyes go away, don't they? How about that? Then it's minus 8i squared. Well, -20i plus 20i gives you 0, right? So these two things just go to 0. Okay. And I squared is -1. So you get 50 plus 8, which is 58. Very easy. Now, it's not the usual thing that these numbers will add up to 0. Your eyes will add up to 0. You're usually going to get an I term. Okay. That's just a coincidence. Gage plotted it that way when he chose 4 and I chose a negative. Okay, he knew that was going to happen. I'd already written down the negative. Makes a good illustration, okay? Okay. Now, adding or subtracting these things is even easier. I'm not even going to go over it. Nobody ever has trouble with it. Okay? So if you have trouble with it, that's great, you're unique, but we'll deal with it, but I don't think you will, okay? I think that's okay to be unique. Dividing complex numbers is a little trickier. Okay, so let's say we got this. To divide these, we do something that's a whole lot like finding a common denominator, but actually easier. Okay. We multiply this by 6 plus 2i over 6 plus 2i. So I'm going to ask you to write that out and see what you get. Now you notice, why do you think I did 6 plus 2i? Because I had 6 minus 2i here. Whatever my imaginary part is here, I write the same thing down, but I change its sign. Okay? And then, of course, I got to multiply numerator and denominator, what I multiply by, has to be the same thing. Okay? So what's that equal? Okay, so you need a little bit of a hint here. You're going to multiply numerators and multiply denominators. Two fractional or rational expressions. And now you're going to use the distributive laws I just illustrated, right? So do the details of the distributive law and see what you get. Okay, first thing you have to understand is why I wrote this down, because when you multiply fractions, you multiply the numerators and you multiply the denominators. It goes back to the numerical fractions that we did at the beginning of the course. And if you're not real clear on how to deal with fractions, you really need to get clear on it, because rational functions are coming up. And those of you who are in the MDE 61 will verify for everybody that fractions develop a lot more attitude very shortly, okay? So you make sure you understand the operations for just basic fractions. And one of them is to multiply two fractions, you multiply the numerators, you multiply the denominators, nothing to it, okay? Now, there might be something to it after you write it out, and there is here. Okay, so if I multiply this out using the distributive law, I'm going to say that's 5 times your 6 plus 2i. Plus 4i times 6 plus 2i. And in the denominator, you're going to have 6 times 6 plus 2i minus 2i times 6 plus 2i. Well then, that comes out easily enough. 5 times 6 plus 2i is 5 times 6 plus 5 times 2i. And you're going to have 4i times 6 here, plus 4i times 2i. Divided by I'm just gonna write it out, it's the same stuff. It's applying the distributive law here. This is what you get. In the numerator, you're gonna have 30 plus 10i plus 24i plus 8i squared. Clearly, 5 times 2i gives you 10i, 4i times 6 gives you 24i, and 4i times 2i, and this is where you gotta be a little careful. 4 times 2 is 8, I times I is I squared. So don't forget that square. You forget it. But, yeah, first time you see it, you make those little mistakes. Okay. Denominator, 6 times 6 is 36, 6 times 2i is 12i. Negative 2i times 6 is negative 12i. And look, the i's go away. Okay? And this wasn't even something that Gage made us do. This always happens. Okay? And then it's plus or minus 4i squared. Okay? Well, 12i and negative 12i adds up to 0. So just okay, that's all be 0. Then we get then 30. 10i and 24i is 34i. And I squared is negative 1. We're almost there. Down here we have 36 minus 4i squared. I squared is negative 1. Minus 4 times negative 1. All the details. Don't make any mistakes. 8 times negative 1 is negative 8. 4 times negative 1 is negative 4, but we have a negative of that, which makes that a positive 4, right? Okay. And if we do this, we're always going to get 2 positive numbers down here. Okay. Now do the multiplication. Don't just assume you're going to get the 2 positive numbers. Work it out until you get really used to it to see why that happens. And finally, 30 minus 8 is 22. We get 22 plus 34i over 40. Of course, now we can write that out as 22 over 40. Plus 34i over 40. And we can reduce these fractions a little bit. We get 11 over 20 plus 17i over 20. Right, there's our complex number. There's our division. Okay. Now, to actually complete this and see where we are, I should have written down this as a second step, and I'm just going to say 5 plus 4i over 6 minus 2i equals this. 6 plus 2i is called the complex conjugate of 6 minus 2i. So whatever your denominator is, you multiply it by the complex conjugate, and you're going to get a real number. Okay. But of course, to multiply this by the complex conjugate, you've also got to multiply the numerator by that complex conjugate of the denominator, because this has to be 1. This is clearly equal to 1. You multiply by this, so we haven't changed this value, so it is equal to this. Okay, we can check this. It's always good to check, and it's always good to get the insight you get from checking, especially here. Okay. A divided by B equals C if A equals B times C, right? Multiply both sides by B, it's obvious. That's what division means. When you divide this, you're trying to find the number that you multiply by this to get this. That's what division is. Okay. How do we check? So we check if this divided by this, which is what we started with, is equal to this, which is what we ended with. Well, if I didn't make any mistakes, there's no guarantee I didn't make any mistakes. I don't think I did, but I wouldn't bet the farm on it. Okay. So I check this. Is this times this equal to this? Okay. This divided by this equals this means this times this equals this. That's exactly what I've got. This times this times this, and it's got to equal to this. Well, so I'm going to go ahead and do the distributive law. I'm skipping steps. Okay, don't want you to skip steps, especially right now, because some of you are still a little bit fuzzy on the distributive law. You want to keep reinforcing what the distributive law tells you. But I multiply this by this. 6 times 11 is 66. So I get 66 over 20. 6, I get choked up on chunk fractions. So 6 times 17 is 102. So 6 times 17I over 20 is 120, 102I over 20. And then we have minus 2I times 11 over 20, which is negative 22I over 20. And then 2 times 17 is 34. So I get negative 34 here, and I get an I times an I, which is an I squared, and that's over 20. Well, this equals 102 minus 22 is 80. So I can put these two multiples of I together, get 80I over 20. And then negative 34I squared. I'm skipping a step. I squared is negative 1. 34 times negative 1 is negative 34. Minus that is a plus 34, and it's over 20. So we get this. 66 and 34 is 100. We have 100 over 20. Might be a little hard to read, but I just copied down my 80I over 20. Well, what's 100 over 20? Hold up fingers. 5, right? And 80 over 20 is 4. So that's 5 plus 4I. Is that what we wanted to get? That we were hoping to get? Yep, there it is. And there it is. A big check mark there. I actually got through that without messing anything up. You know, probably ought to have a celebration or something. Okay. So you got to remember what to do to divide these things. And there are a lot of steps, especially if you're writing it out completely, as I really hope you do, so you'll remember what you did. But it's not difficult, it's just, a little tedious. Now, there's much more I could say about all this, but that's basics.